Hello friends, welcome to my channel. This is the first video in Conjugate Heat Transfer series. In this video, I will present the procedure to pre-process the conjugate heat transfer problem in SimFlow and OpenFoam12. Watch the video till the end. Please do like, share and subscribe. So let's start. In this video, I will discuss in detail the case setup procedure for a conjugate heat transfer problem. I will discuss two methods, method 1 using SimFlow-GUI and method 2 using manual method using OpenFoam12. For this purpose, I will model a simple conjugate heat transfer flow scenario, the flow over hot cylinder in a rectangular duct. As you know, conjugate heat transfer is a process in which the heat flows from fluids to solids and vice versa. The process of heat transfer within fluids is called convection, and the process of heat transfer within solids is called conduction. The interfacial heat transfer is complex and it is based on interfacial coupling and other parameters. The conjugate heat transfer is a natural phenomenon which occurs everywhere around us. It has specific applications in industries like heating, drying in food processing industry, body in white baking process in automotive sector, and in other industries such as aerospace, HVAC, heating, ventilation and air conditioning, etc. In this tutorial, the geometry is created in Salome. A rectangular duct with a cylinder are modeled. In the first method, pre-processing and simulation are carried out with SimFlow graphical user interface and the plugged-in OpenFoam12 version. In the second method, pre-processing and simulation are carried out in manual mode using OpenFoam12 in Windows subsystem for Linux. ParaView is used for post-processing. Please watch the video till the end. Do like, share and subscribe. Now let us start geometry creation. A rectangular duct of size 4 meters by 1 meter by 1 meter is created. A cylinder of diameter 0.5 meters and length 0.2 meters is created and located centrally in the duct. Note that the main objective is to discuss the conjugate heat transfer problem case setup procedure in SimFlow-GUI and manually for OpenFoam12 simulation. The flow through inlet passes over the hot cylinder in this simulation. For SimFlow simulation, the duct geometry is to be exported in step format. However, the cylinder geometry can be exported in STL format. For OpenFoam12, that is for the method 2 simulation using OpenFoam12, further processing is needed for duct geometry. This includes creating the face groups, inlet, outlet and walls. Export all the three groups as STL files. Then append the data from three files to a single file and name it as fluid.stl. While working on geometry, I will show this process. Let's jump over to geometry creation. Now let us start creating the geometry in Salome. I have already created it. I will show the process. Okay, so I loaded it. This is the duct, rectangular duct of 4 meters in length, 1 meter in Y and Z directions each. So in X direction it is 4 meters. Let us color it. Okay, now This is a cylinder which I created. I'll make it transparent. This is a cylinder which is created. The cylinder diameter is 0.5 meters and length is 0.2. Now it is located here. Now we need to translate it to this location. Okay, now the translation coordinates are, I'll show you. I'll take the geometry, operation, transformation, translate. Now here the dx is 2 meters, dy 0.5 and dz 0.5. You can see now, once this is done, the cylinder is relocated to this position. Okay, fine. So I'll delete this anyway, I have one. Okay, now once this is done, we'll save the cylinder, we'll save the translation as STL file. Export STL. So I'll name it as solid. Okay, then I will save the box in step format first. Reason is, when we set up the case in SimFlow, we need the box in step format, so I export it in step format. So I'll name it as Duct. Done. So two files are created. Now for setting up the case in OpenFoam12 Windows subsystem for Linux directly, we need to modify the box geometry. The reason is, here we have to do the grouping and all in manual mode, so we need to process this geometry further. So what we do is, we explode this geometry into faces first. Okay, now let us take this face, hide it, then go to this face, hide it. These are the 4 faces. So go here and bring a comp wall. So you can see the wall group is set. Now the first face, remove this, I will hide this, and the face 1 is inlet. Rename it as inlet, and then the last face is outlet. Rename this as outlet. Okay, now this is the one. Right. Then we save these files as STL files. Export STL. So this is inlet, outlet, and then wall. So now I'll show you here. This is the wall and inlet and outlet. So the wall geometry, so this is inlet. The flow enters here and passes over the cylinder to outlet. This grouping is created to set up the case in Windows subsystem for Linux. Now in the next step, we create a single STL for duct by appending the inlet, outlet and wall STLs. So we stop this process here and go to the next step. Now this is a folder of geometry. So take this inlet, copy, paste it, and rename this as fluid. Now open this file in text. Okay, now So this is inlet, INLT. This is inlet. Okay, now open outlet. Add this outlet here. Now copy this and paste below this. Now close this. Open wall. Add wall here. Copy this text and add below. So this is the fluid geometry, where all the groups are identified. Now for Windows subsystem, we use this fluid and solid as two geometries. So now we have created the geometry for pre-processing in Windows subsystem for Linux, OpenFoam12 direct simulation, and pre-processing the case in SimFlow graphical user interface. Now we'll proceed further. Having done with geometry creation, let us start with pre-processing in SimFlow. Here, evaluation version of SimFlow-GUI is used. I have briefly discussed the pre-processing procedure for conjugate heat transfer application. I have used the SimFlow reference tutorial. The link is given here. One can go through this tutorial for further details. I have used this tutorial to understand the procedure and set up this case. Now compared to setup procedure for single region, the procedure for conjugate heat transfer case includes additionally generating mesh for different regions, creating subregion groups such as fluid and solid, linking of interface between regions, and updating operating parameters for each region separately. While setting up the case, I will discuss this further. Now, the working fluid water at 300 Kelvin passes through the cylinder, which is at 400 Kelvin. The maximum cell count I could use is 65 by 30 by 30 cells in X, Y and Z directions with one level of refinement around the cylinder. This is because as I am using evaluation version, I could not use the cell size finer than this. Now let's launch SimFlow-GUI and proceed. Open SimFlow, click new and add the case name and click create. Now load the geometry, select the file duct.step and solid and load both the files. Click OK. So the units are in meters. So this is the geometry loaded, duct and the cylinder which is inside it. You can check both the geometries once. So this is a solid and this is the duct. Now we go to grouping. Click the field duct and then Windows button. Then there are 6 faces. Now create the inlet, outlet and wall in a usual process. So this is inlet. Then create the outlet. Now select all the other 4 faces and create the wall group. You can see all the 4 groups here. Rename them. Group 1 as inlet, group 2 as outlet, and group 3 wall. Solid we can leave as it is. because it is only one face. Now go to hex meshing, click the refinement and add one level. For duct there is no need. For solid, again click the refinement, add the refinement as 1. Okay, then go to base, click auto size, the geometry will be fitted there. Then give the mesh number 65 divisions in X, 30 divisions in Y and 30 divisions in Z directions. Okay, then we go to point. Now we need to create a point in the duct region outside the cylinder. So select 1 in X, 0.5 for Y and 0.6 for Z. So the point is created inside the duct and outside the cylinder, the object. So then go to mesh and create mesh. Now the mesh is generated, you can see here. So change the duct inlet and outlet to patch mode. For duct wall and solid, no need to change. Then go to default. Now we have to change the default mesh and we create a sub-region. Rename the sub-region as fluid and click OK. So this should be a fluid. Now we have created the mesh for the duct. Now we have to create the mesh in the cylinder or the object solid. Go to base. Now here the same number of the mesh divisions are used. Go to mesh point. Here we should keep the point inside the cylinder. So change X to 2 so that the mesh point goes inside the cylinder. You can see the point is inside. Now go to mesh and click meshing. So the meshing is done for the solid. Now here there is solid in default and solid in fluid. Now we have to change the default to solid. Here click the make subregion and change the name to solid and click OK. Change the solid to solid mode. Okay. Now once this is done, we have two solids, solid in fluid and solid in solid. Select both. Then a button will appear at the top. Just click it so that the interface between the fluid and solid is generated. Now once this is done, we are ready for setting up the case. Go to setup. Then we select CHT multi-region. So it is a steady state, transient simulation compressible solver with conjugate heat transfer, buoyancy, turbulence, radiation. So click select. Okay. Now you go to radiation, we switch off radiation. Next click turbulence, select RANS and KF7 model is okay. Now go to thermo. We need to add the fluid properties. So for fluid, go to material database and select water. Click apply. Then select solid. Go to material database and click steel. Select apply. So the material database is done. Now we go to operating conditions. It's okay. cellZone. And these are boundary conditions. Before that, we need to go to solution, check this. If we want to change anything, we can change here. For pimple, the number of auto corrections and all the parameters we can set here. So for the duct, we select velocity inlet and 0.1 meters per second. Okay, we need to change the thermal properties also. The temperature, inlet temperature water is 100 and turbulence parameters you can retain. Then go to outlet, select pressure outlet. And all the parameters can remain the same. Now go to duct wall. This wall, no need to change anything there. There is no slip boundary, and these two are the interfaces, no need to touch that. So now go to initial conditions, click fluid. The temperature, initial temperature is 300 Kelvin. So for solid we set temperature as 400 Kelvin. So heat transfer takes place from solid to liquid. Now go to run, fix simulation time as 180 seconds, fix the time step and set the time step as 1 equal minus 2. Output for every 5 seconds. Then we go with serial mode only and save the case files and launch the simulation. So the simulation is started and you can see the residuals dropping. So as the time step is 1 equal minus 2 and we have to run for 180 seconds, it will take around 3 to 4 hours on single processor. So we will wait for the results. I have already run the simulation, so I will load the files and show the post-processing methods. I have loaded the earlier run simulations. The simulation was run for 180 seconds and you can see the residuals have dropped well. So we go to post processing and then click the ParaView. So it is already open here. Click apply. So this is the domain. Let us create a section in Z direction. Okay. So this is it. We will go to velocity. You can see. So this is the velocity contour at 180 seconds. Then you go to temperature. Set the limit to 310. And select turbo here. And the fluid is flowing over the hot cylinder. The temperature is convected through the fluid. Okay. So I will create an animation and show it. Now let us proceed to method 2, pre-processing manually and launching the case in OpenFoam12 in Windows subsystem for Linux. First, let us compare the folder structure for normal and CHT simulations in OpenFoam12. The pre-processing of normal CFD simulation in OpenFoam12 contains three folders: 0, constant, and system. The folder 0 contains the following files. These are state variables for the simulation, and the respective details are provided in these files. The second folder is constant. In this folder, another subfolder called trisurface is added, where the geometry files are saved. And then we have a list of files for fluid properties like transport property, turbulence properties, and other details based on the model used. The third folder is system. In this folder, the files include blockMesh dig, which is used for creating the out-of-box domain, then control dig, where the simulation details are listed like start time, end time, save frequency, and all other details. And other files include the finite volume schemes and solutions, and then snappyHexMesh. This is the file where the details of meshing, refinement, and other details are listed. So this folder contains all these files. Based on the model's requirements, the file list may change. So this is the folder structure for normal CFD simulation. Now let's check for a CFD simulation of conjugate heat transfer. Now again here too, the folder structure contains three folders: 0, constant, and system. However, in 0 folder, you have two subfolders for fluid and solid. So the subfolder for fluid contains again the files related to the state variables, and the subfolder solid contains the file related to temperature. So here, as it is a conjugate heat transfer simulation, in solid we are solving the temperature, the conduction equation, so the details are given in this file T. The next folder is constant. Here too, the basic, you have three folders. One is geometry, where all the STL files are listed here. The second folder is fluid. In this folder again, the details of momentum transport, physical properties, turbulence properties, radiation properties, gravity, and other details are provided. In the subfolder solid, the details of physical properties of the solids are provided. Then you have the next folder system. Here the fluid, again in the subfolder fluid, the files for finite volume schemes and solutions are provided, which are used for simulation in fluid region. Then the same files are provided for solid region in subfolder solid. Then a list of files are provided here, that is blockMesh dig, control dig, and other files as in the normal simulation case. At the same time, if the case has to be run in parallel mode, we need additional files like decompose, pad, dig, and all. So depending on the parallel or serial mode simulation, depending on different models we are using, the list of files in these folders may be added. Now for this simulation, I have selected the tutorial case heated duct to start the setup for CHT simulation of our case. So the link or the path of the tutorial is given here under. Now let's start on the manual method. So this is the folder structure which I took from OpenFoam tutorial heated duct. So the folder contains three required folders: 0, constant, system along with two bash files. Okay, now this folder is created by me. Just I copied the same files here for safety. Okay, now first of all let us surf each folder and see what we need and what we can delete. First go to 0 folder. Here we can see 3 folders: fluid, heater and metal. In this case a heater is there where the heating is generated, which is transferred to the metal and then to the fluid. Now we don't need here one of them, so we delete heater. And rename the metal as solid. Okay, we'll come back to this folder later. Let's go to other folder, constant. So here too we have fluid, heater and metal. So let us remove this heater here and rename this folder as solid. Now in geometry we need to copy the STL files which we need to use for our case. So I'll copy those files here now. Okay, I have created the geometry in this folder. So let us select the files which we need for this simulation. So here we need fluid and solid. Let us copy these two files and save here. Now let us delete these 3 files. Okay, now here if you see fluid, it is the duct domain which is treated as fluid. As I explained you earlier, this file is a modified file where all the individual STL files are copied here. Like this is inlet, so this data is copied from the inlet STL file, and this data is copied from the outlet STL file. So this is the folder. So inlet, outlet and wall. Okay, so these data from these 3 files is copied to this fluid file. So this is the grouping we do here in manual mode. So this is the data from the STL file wall. So this is the modification we have done here for fluid file. So the solid file, which represents the cylinder in the duct, no change is needed. So now this part is done. We'll go to solid. Here the physical properties, we'll come back to this later. In this step no need to change anything here now. Okay, now let us go to system folder. Now in this folder again delete this heater and rename this metal as solid. Now open folder fluid, open these 2 files and check if we need to delete any data here or a matter or a word or something. So here it is fluid, and let us not touch this part. We'll revisit this file again while selecting the turbulence model. So now we can close this, open this file. So it is fluid. Okay, no need to change here currently. Fine. Now open solid. Let us check these 2 files. Now again here we see metal. Remove this and write solid. Nothing else to change here. change this to solid. Okay, so here we have modified the files. So this folder is over. Having done the modification so far, we will proceed further. Now let us check these files and modify the data here. Now first select blockMesh Duct. In this file, we need to change this data. So these are 8 points. So these are the coordinates of 8 vertices of the bounding geometry in the simulation. In our case, it is duct. In Salome, we need to extract the coordinates of these points and paste here. So I have done that already. So I'll paste the data here. I copy from here. Okay, because it is in meters, so conversion value I kept 1. So this is it. And here we need to give the number of cells in XYZ directions. So in our simulation I have used 65, 30 in Y direction and 30 in Z direction. So this file is done. However, it will be good if we check if these coordinates are correct or not. So for doing that, I will open the terminal. So I will set the path to the working directory. And I will use the command blockMesh. So here you can see it is done well. The geometry is bounding, and if you see this end, that means that the process is fine. So the data which we have copied and pasted here is fine. Otherwise, we need to revisit the geometry and check the coordinates and modify this file till we see this result. Okay. Now this file is done. We will go to control Duct. In this file, we need to remove this heater. This is solid. Okay. Here no need to change anything, but in my simulation the end time is 180, and I don't want to change anything here. When I close this file, I go to next file. This file is needed if we run the simulation in parallel. Generally I use 2 processors. Okay. So nothing else to change here. Now this file FV solution. Pimple is the solver. We will revisit this file if needed again. Currently no need to change anything here. Now mesh quality Duct. Here too there is no need to change anything. Now snappyHexMesh. This is the main file which we need to modify. Okay, so here the first step. This is fine up to here. Geometry. So this is the fluid. We need to add the information of our geometry files here. So this is fluid. The same we need to put here. And the file fluid contains 3 groups, so we need to add the information of those 3 boundary groups here. This is inlet, then we have outlet, and the last one is wall. This part is done. This is metal to heater and fluid to metal. So I remove this. Now here we have fluid to metal. I show this is interface. So what I do here is I will write the solid. Okay, this part is done. Now here again we need to change fluid, and we need to update the groups here. Inlet, outlet, wall, so this is done. So here fluid to metal, alright, solid. For creating the mesh within the solid, we need to give a point, a reference point here. So that point is 2, 0.5, and here I put 0.6. You can select any point within solid. Copy this. Okay, now here this metal to heater can be deleted, and this is the inside point for the fluid domain. So here I put 1. So this point is inside the fluid domain and outside the solid. Okay, so this is what we need to do here, and everything is done. Let us check again. So this part is done correctly. Geometry is fluid, fluid STL, 3 groups, inlet, outlet, wall, fine, and solid. Okay, we can increase the levels also here if we need finer mesh. So this is solid, and this patch information is fine. Okay, you can add the number of cell levels also here. I go with the basic one now. Okay, so this file is done. One more thing, yeah. So generally manual process is prone to errors. Let me revisit this file and show the error to you. Here I forgot one thing. Here the patch information. So here the patch information we have to write wall. This is the problem with manual modifications. Here the role of GUI comes into picture. Such errors will be eliminated. Okay, so now this file is fine. So in this folder we have corrected everything, modified everything. So now we have completed step 2. Let us progress to step 3 modification. We will go to system folder again. Now in our simulation we have used turbulence model. We need to update the turbulence parameters now. So open this system folder and go to fluid. So here we need to change the information now suitable for turbulence model. So in this case, these schemes are to be modified. So I have already done that, so I will copy that data here. Then, so here you see K epsilon information is added here. Rest is fine, so we can close this file now. Now open this file. Yeah, so this information has to be modified here. So I have taken data from another tutorial and I am copy pasting here. So I copy from here up to this point. Then for pimple solver, we will modify this also. So this is it. So again you get here K and epsilon. Let me repeat. I have copied this information from another tutorials of OpenFoam12. This file is done. Close this. Now we go to solid folder. So open this file. Let's see here. In this file, again we need to change this part, rest being same. I don't see much difference even if we don't use this, but I have added it for safety because turbulence model doesn't affect here, but still I modified this. Okay, now open this file. So this file seems to be fine, no need to change anything here. This is solid. Okay, no need to change anything in this file. Yeah. Now let us open this file and see if we have to change anything. So for pimple solver, we need to add the characters. Okay, so this is fine. We close this. Nothing else is to be changed here. So in this folder, the turbulence related information is updated. Now we go to next folder, constant. So this is because I have launched the case to test the blockMesh. So I delete this polymesh folder. Okay, now let us open this folder. So here we need to add the turbulence properties file. So this file is needed. This file I copied from another tutorial. Let us open this and check. So yeah, so here for K epsilon, this is the data we need to add, and this is fine. And in G, there is no need to change anything. Momentum transport. Okay, Here laminar is given, we need to update this information here. So this is for KX run model, turbulence is odd and print coefficients are on. Okay, so we can close this. Physical properties. No need to change anything here. Let me check once again. Okay, so this is fine. The fluid folder is done. Go to solid. This is the folder for solid aluminum. So let me check. We need to change it to steel. Okay, because in our simulation we have used steel, so steel material properties are added here. I forgot to update this earlier. Okay, so solid part is done. So in this folder nothing else is to be modified. Now we go to 0 folder, fluid. Now here, as we are solving turbulence, the files related to turbulence parameters are to be added here to update the boundary conditions. So we need 4 files. So I copy those files and paste here. Now, before updating the files in this folder, we will cross-check other details once. I would like to make few points here. First thing is, here these files are related to boundary conditions. Before updating this, it would be better if we check the mesh details, whether the meshing is done correctly or not. So we will first check that, then we will come back to this folder and modify this. To do that, we will go back to system folder first and let us check this once. Now we have taken the basic case files from the tutorial heated duct and modified it. It may be noted that we have seen metal in that. So we have modified metal to solid. So exclusively wherever metal is there, I have modified it, but still there might be some locations where we might have forgotten. This is very important to check. Let us go to this file only, because this is the file where the metal is modified and the mesh data is given. So in this, now here let us check the word metal. This is always better to check from find option metal. See here. So we have forgotten this. So for solid, the phase zone is solid only, and the cell zone also you just write as solid. So there is no heater here, we have removed it completely, but better to check once. So done. Okay, now once this is done, first of all let us check if the mesh is working correctly or not. So open the terminal and set the path to the working directory, and now once again let us mesh it and check. The first command is blockMesh. So this is done correctly. Then we go to snappyHexMesh, overwrite. This should give some errors if there are any. Now it is running well as of now without any errors. So now this is done. We get end here. So this command has worked well. Now we go to next command, split mesh regions, cellZones, default name is fluid. Oh, okay. So let us see this command. Now with this command we are splitting the regions and we are creating the interfaces also. So here, now you can see here, this has worked well. So it has created two regions. Now checking this at this point before updating the boundary conditions is very important. The advantage of this is, see here, two interfaces are created, fluid to solid and solid to fluid, and these two interfaces need to be used in the boundary conditions. That is the reason why I tried to do this meshing at this point. Okay, now once we are fine here, everything is fine. So we check here, when we run these two commands, what we notice is, see here you get cellZone, and here polymesh and cellZone, and within the fluid also you see for polymesh. So here in fluid, when you open this polymesh, the boundary face, this file, so the patch information is given, and you see here the fluid to solid interface is created here. This is very important. Then in the solid zone, open this file and check. Here too you can see the solid to fluid interface is created. So this boundary condition has to be used in the solid. I will show you that. Now it is fine. Now we go to 0 folder, fluid. Here too you can see cell to region is created. No need to change this, no need to open this. Now we will start updating the files from U. Open this file U. Now here you can see fluid inlet. So this is inlet for us in our case, and this is outlet. Fine. So here already in the earlier tutorial case it is written here fluid to metal, but it is not so. It is fluid to solid. I have shown you this here in the command. You can see fluid to solid. This is the interface. So this name we have to write here. Now this is solid, but we have wall as well in our group. So we add the wall here, and again it is a no slip boundary. So just write wall. And uniform, this is the internal field, and inlet velocity boundary is given here. So here the velocity in x direction is 0.1, and I set this to z direction to 0, and the flow field is initialized in z direction. So I will copy this and I will initialize in the x direction. We may take all zeros here, but it's better to have the value. Okay, Now this file is done. We have all the 4 boundaries: inlet, outlet, wall, and this fluid to solid interface. Okay, then go to T, temperature boundary condition in fluid. Here too, the flow field is initialized with 300. Fine. Now fluid to inlet, we need to change this boundary to inlet, I, and here is outlet. So here again it is fluid to metal, it is solid. Again we need to use the same name, and again we have here wall. But the value, the type should be modified here. Let me check this. 0 gradient. Okay, so rest of the parameters are fine here. Okay, now go to PRGH. So we need to modify this to outlet, and here there is no need to change anything else. Now go to pressure. Dimensions, internal field uniform. So fine, no need to change anything here again. Go to this file. We have this fluid to solid, inlet, outlet, wall. I have taken this file from a tutorial where the same names are used, luckily. Okay, so here there is no need to change, everything is fine. Wall, outlet, inlet, and fluid to solid. Okay, now close this. Go to KF7. I think here too same boundary names will be there. Yes, so fluid to solid is the interface, inlet, outlet, and wall. So no need to change anything here too. Now epsilon, fluid to solid, inlet, outlet, and wall. Okay, fine. So no need to change anything. This file is created due to the mesh generation, so no need to open that. Go to this file. Yeah, so same fluid, inlet, outlet, and wall. So here too there is nothing to change. Yes. So all the files in this folder are updated. Now go back to solid. Here again this file is created due to meshing, so we neglect that, we ignore that. Now we go to file temperature. The solid domain is maintained at initially at 400 Kelvin. Modify this to 400. Then in this metal, we'll change this metal to solid. Then this is fine, metal to fluid. Now here in this, metal to heater can be deleted because we are not using any heater here. Okay, now metal to fluid, again here we need to use solid to fluid. Remove this metal, right, solid. Okay, so everything is updated here. Now let us go to simulation terminal and launch the case and see how it goes. The command is CHT. So here we see field T of type coupled temperature cannot apply patch. Field T. Okay. Well, yeah. So I made a mistake here. This should be 0 gradient should be written for wall. Instead I wrote it for fluid to solid. So like this and modify this. Okay, this is the mistake. The rest is fine. Now let us launch it again. Yeah, so now the case is running. Let us see if it is solving the k epsilon or not. Stop this a while. Just hold this. You can see if it is solving for k epsilon or not. So you can see here k and epsilon are solved. Yeah. So it will take long time because I launched the case on one processor. So I will show the results once the simulation is done. The simulations progressed well and completed 180 seconds successfully. Before progressing to ParaView, let us check the folders here. We have a file here, all run. Let us open and check that file once. Okay, so till this point we have done. As we have run the simulation in serial mode, we don't need these three, but we will use this command so that it will create some additional files. Let us see them. Touch all. Okay, now once this command is run, you can see some additional files are created for fluid and solid regions. Now we can open ParaFoam. Let us delete this file and load the files for fluid and solid. Apply. Okay, now this is the file for fluid. This is for solid. Okay, let us change the color of this solid. So you can see the mesh refinement is not enough. So we need to increase the cells so that we have a fine mesh here. Of course, this is a demo case, so no need to worry about that now. Now let us create a clip and see the inner part of the fluid domain. Apply. So now here you can see this solid part, and you click, you can see the solid part here. Now I delete this clip. Now I will create a section and plot the temperature contour. I will create the section in Z direction. Click OK. Okay. select temperature and plot the last result. Set the temperature scale from 300 to 310. And we can change the contour color to turbo. Okay, now you can see the diffusion of temperature and the convection of temperature into the fluid zone. Well, the mesh is not finer enough to see a clear circular cylinder here. For this demo purpose, this seems to be fine. The main objective is to discuss the procedure to set up the CHT case. So this is the contour plot of temperature. Accordingly, we can plot the contour of velocity. This is it. I can again change to turbo. Fine. So I will plot animation of temperature and present it here. The animations created from both the simulations are presented here. In the downstream of the cylinder, the convection of temperature in fluid region can be seen. There seems to be slight difference due to mesh refinement near the cylinder in this region. Further, finer mesh near cylinder and fluid interface will give better convection in the fluid region. However, as the main objective of this tutorial is to discuss the procedure to set up conjugate heat transfer case in OpenFoam12, I used mesh. Finally, the procedure for pre-processing a conjugate heat transfer case using SimFlow graphical user interface and manual method are discussed in this tutorial clearly. Further, the geometry modification needed to pre-process the case in OpenFoam is clearly explained here. I hope this video helped you all. Should you have any queries, please leave a comment in the comment section. I will try to help you out. Thank you for watching my videos. Please like, share and subscribe, and do not forget to click the bell icon.